record on this computer. Okay, I think we're recording. Wait, that's my grade. Wait. Hold on, that's my program.
I mean, that's not that bad, man. 87 is not that bad. You could just slightly be showing off, you know?
No, I was not thinking while I was sharing. Okay, hold on.
I think I have the exact same grade though.
That was for my CS2 class though. That wasn't even for this class.
Oh.
Okay, now let's try sharing it again. All right, let's see. Okay, now let's record. Oh, it's still recording? Ah, oh, god damn it. Whatever. Okay, anyway. Let's see. Thank you for the Minecraft music in the background.
Oh, that's actually the playlist that they sent in.
Oh, is that?
Yeah. Is it too loud? Should I pause it?
No, it's good.
All right.
It's good. I was just messing with you. Okay. So let's open up the whiteboard here as well. And everything. Let's see. Let's just. Yeah.
Where are we starting is my question. What lecture?
I was thinking in starting with, where did they say this test is going to be from chapters 26 through 29. I was going to try to find where we started chapter 26, but then I realized that most of his lectures are not labeled.
No, they're not, but there are some that say chapter blank.
Yeah.
So just find one that says chapter something, and then we'll and then we'll find out. Chapter 29 is lecture 21.
Okay, so that's lecture 21 is chapter 29. So let's. Lecture 8 is way too back. Hold on. Okay, chapter 26. Oh, there we go. Perfect. Okay.
What lecture?
Lecture 12.
Oh my god, we got so much to go through.
We've got a lot to go through. Let me get my textbook out because the textbook also has some pretty good explanations.
It's true. There is a lot of noise on your end. Is there any way you could?
Sorry, here. Let me try like. Hold on a second. Let's see.
My bad. Where are the Zoom settings? I see no settings on Zoom.
Okay. How does that sound? Does that sound a little bit better? Maybe.
Yeah.
If I lower the sensitivity, it's going back up. What?
No. Here you can go to your mute button at the bottom left, click it, and then go to audio settings.
Okay, hold on. All right. Oh, Alice is trying to join. Welcome, Alice. Right here, and I go where? Audio settings?
Yeah. And then suppress background noise. Make it medium or high.
Oh, gotcha. There
and
you
make
go.
sure to turn off automatically adjust microphone volume.
Ah, there we go. I'll just put that there or something. How's that sound?
Better.
Okay, awesome. Okay, so lecture 12. Chapter 26. What is something that we want to keep in mind with this chapter.
Oh my god.
So I feel like this is kind of like anyway. This is finding the potential from an electric field. So the electric field and the electric potential are somewhat connected, but they're two different perspectives on how source charges change the space around them.
Are you reading off the textbook or?
Yeah,
Okay.
just from what I'm seeing here. So electric potential can be found if you know the electric field, and the electric field can be found if you know the electric potential. So it's one or the other. Electric field lines are always perpendicular to equipotential surfaces. Okay, holy shit.
Yep.
Now this is picking up fast. Okay. They don't have any drawings. Why aren't there any drawings? I need pictures.
If you scroll down to page 9, that's what they're talking about.
There we go.
Right
Look
there.
at that. We already made it all the way to slide 9. Look at us making progress. Oh man. Okay, well, we should probably look at the more proof stuff they have. So let's see. My God. Okay. It looks like with this, finding the potential from the electric field, you have in this instance, oh, this is actually, I think this is from the textbook. We had an example. The pages don't stick together. So he actually cuts out quite a bit here that, wait. Oh, okay. This is something else. This is something else. So when you see this equation kind of drawn out, it's actually a lot better than it is made out to be, I think. Although I don't know how important this is, that I will say, but this is a way of practicing. So let's see.
We did use that equation in one of the past homeworks,
Oh, okay.
so I think it'll come up again.
So with this, we want to keep in mind that the electric field inside a capacitor is found with this equation, right? It goes Q over epsilon naught times the area. So we're using this picture as our reference. So we want to integrate. So here, let me read this. The capacitor establishes a point P, this right here. And we want to find the potential at that point. We've chosen the S-axis measured from the negative plate, which is the 0 point of the potential. So in a way, I is also our 0 point of the potential. What we want to do is we want to integrate along the S-axis from SI initial being 0. So SI is 0. So this is where VI is also 0. And then S final is going to be S. So it looks like this is moving from here to here.
S final's D as well.
Do they have it written as D here?
They do, yeah. If you look at the x-axis.
Oh, okay. Well, that would probably be if they have
no,
it go
you're
all
right.
the way.
You're right. Sorry.
Yeah, yeah. That's if they go all the way, which we can do that as well. But well, let's start with this one first, I think. Now let's see. So the way the equation gets written is you have VS. What does VS stand for? I don't know. Velocity, I'm assuming, or something. You want to have it, you want to integrate along the S-axis. And you want to notice that the electric field points in the negative S direction, meaning that E in terms of S is acting in a negative Q over epsilon naught area. Right? So what we get here, actually, let's just ignore this part. What we're getting here then becomes that, why is that so thick? Okay, hold on. This goes velocity S is equal to velocity final. I'm saying velocity, but I'm assuming that's what it is. I'm not entirely sure.
It's probably voltage.
Voltage, that's the word.
Yeah.
So minus the integral of 0 to S of the electric field d of S. So the way that this is going to end up looking is it's going to go like, well, I think the initial voltage is kind of just 0, as you see this right here. So this turns out to be 0. So then what you're stuck with is negative E integral 0 S ds. And so what this kind of becomes is negative E S. And then that goes to negative Q over epsilon naught alpha S. And that just turns out to be positive. That's your equation. Or if you want to simplify it all the way, ES is your equation. Pretty straightforward, thankfully. That makes sense, at least. Let's hope it stays that way. Alrighty. So voltage equals ES is the capacitor potential we deduced in chapter 25 by working directly with the potential energy. The potential here increases linearly, as we move across the capacitor. From 0 to the electric V equals ED, like you were kind of saying earlier. We found the potential by explicitly recognizing the potential. So, I hate the new update on this thing. So this. So potential energy increases linearly across the capacitor. From V0, and then potential energy here is going to be V is equal to electric field times D, which is D all the way to the side. Any questions? Awesome, because I don't know how much I can elaborate on that one. And it looks like he kind of does it here in a way.
Yeah, no, he did the exact same thing.
Yeah, he does it a little bit. Oh yeah, basically, except he says dx, so it can make it a little bit confusing in class, I think. Finding the potential of a point charge. All right. Let's see if we have anything in the book with it. VB minus VA equals negative. So, okay, do we have something like this in the textbook? Let's see. No, we don't. So with this, you have voltage final minus initial, I'm guessing, equals negative E times DL. We get, this is E right here, I think. Wait, is this E? Yeah. Except it's 4 pi epsilon naught. I don't really understand that part, but identify the point at which to find the potential. This is the position F at S sub F equals R.
That equation is the electric field for a
Oh,
point charge.
gotcha.
The one earlier is only for plate capacitors.
Gotcha. That's right. I knew that looked familiar. Okay. And then I'm assuming the Q over S squared is what the integral of DL turns out to be. Okay. Chill. Sorry, I'm also having dinner while I do this. All right. Voltage at R, or the potential difference here of voltage, seems like it goes from infinity to R.
Yeah. So if you look at the integral on the first line, it goes B minus A.
Mm-hmm.
And then on the left side, you have the voltage at B minus the voltage at A. So if you then look at the line below that, right, the one where it's V of R, they're assuming that the voltage at a distance A is 0 because they're assuming that the point is infinity, which is why it goes, which is why it says infinity.
Gotcha.
And then that means that B equals R. So the voltage at some point R is the same thing as that equation.
Gotcha. Okay.
They just replace the variables is all.
Yeah, that's quite a perspective shift, though. But okay. It looks like here you're integrating in terms of D of S, and that just becomes Q over R, I guess. So yeah, establish a coordinate axis along which electric field is known. Choose the 0 point of the potential. In this case, the position I is at S equals infinity, and then you integrate along the S axis. Okay, I see. So that kind of keeps it. So you only have one here, or whatever. Find the potential at the center of the solid sphere of radius R, which carries a uniformly distributed charge. So solid sphere, that is way too big. Solid sphere. Let's say let's just go like this, yeah. Like that. That's our solid sphere. And let's see. Find the potential at the center of the solid sphere of radius R, which carries a uniformly distributed charge Q. And then we also have our point R. R, capital R. Set the reference point to infinity. Okay. So this looks like it's kind of like a similar approach to our last question. So use Gauss's law, which if I'm right, isn't that the integral? Was it EDA or something like that? Times Q enclosed over
Epsilon not.
was the epsilon not?
I think so.
Gauss's law. I mean, it's probably gonna. Oh, look at you, epsilon naught. Yep. Okay. Anyway, Gauss's law. You end up with electric field of whatever the area of a sphere is, was like 4 pi. What is the volume of a sphere? Or volume or surface area? Let's see. Take integral along the radius from infinity to 0. We'll erase this in the meantime. You know, I thought this review was going to be a little bit easier than what we're looking at.
Um, when he has equations like those, like the ones at the top of that page,
Uh-huh.
I think it's a lot of work to derive them. So what I usually do is I just write it down somewhere, accept the result because that's the result, and then look at how to solve the actual problem. Because I have no idea how to derive those equations, but I do know how to set up the problem, which is what that v0 minus v infinity is.
That's true. All right, so v0 minus v infinity. We have from radius to infinity, and that is subtracted by the internal, it looks like 0 to the radius of the sphere. So in that instance, d of L is what in this case? Is that what is d of L in this case?
I don't know, but I'm tempted to say it's one of the R's.
Yeah, let's see. So you plug this in for this is R to 0. So this is all of that. This is infinity to R. So all of this, right? So we are subtracting this from all of this.
We're adding them both actually, and then taking the negative of that would be the easiest way to think of it.
Yeah, I could. Okay, yeah. And
Because
so
if you distribute out the negative sign, you get you get that calculus thing where you can add the integrals if they have the same endpoint. So this can you can look at it as one integral from 0 to infinity, but we have to split it in half because the equation for E is different at in two different regions.
okay. So this right here, because this is R to infinity, this would be this formula here,
Right.
because this is for R being greater than capital R, and then this formula would be this one up here.
Yeah. And do you see how if you take out the negatives, they both like have the connection at R?
Yeah,
Yeah.
yeah, I can see that.
Cool.
Okay. And so after that, I'm just guessing you pull out the E's, integrate in terms of L. And so in this case, you're going to have the 0 to R Q 4 pi epsilon 0 R cubed times L time over R. Okay, wait. Let's write this down. Okay, left hand side. Let's do the left hand side first. It's infinity to R. That's going to be E times DL. And that's going to be equal to, let's just write the integral again with the actual signs. R to infinity, this one over here. So that's going to be Q over 4 pi epsilon naught R squared times DL. So if we integrate it, we get should also be like this R squared. So this will be f of B. So we get Q over 4 pi epsilon naught R, because you get R there, minus Q over 4 pi epsilon naught time R squared times infinity. I don't think that. I see what you're saying with the integration being weird.
Yeah, I'm trying to work it out as well. And no clue.
Okay. Hmm. Yeah, let's see. Huh. Inductor equals static electrostatic equilibrium. Yeah, his textbook doesn't have a lot of material on this, it looks like. Okay. I think huh. As long as you could get partial credit on this, I think, damn it, I don't know. I don't know what to do with this. We get 3Q 8 pi E naught R, which I guess somewhat makes sense. Over here, R0 E DL becomes Q over 4 pi epsilon naught R cubed times, we have f of b 0 minus f of a, which is the same thing, So this ends up. So this is I'm presuming infinity. I don't really know what else this one down here is going to be. This is going to be 0. This right here. Then we're gonna. Let's say we're adding them. Q over 4 pi epsilon naught r minus Q over 4 pi epsilon naught r squared times infinity minus Q over 4 pi epsilon r cubed. This is definitely wrong.
I got the result. If you
Oh,
want
how'd
to
you do
see
it?
me work it out.
Sure, yeah, here, I'll stop sharing my screen.
I have to get on my my iPad, so give me
Oh.
1 second.
Oh, okay, yeah. All right.
Oh, only the host can show the thingamabobs.
All right, now you should be good.
Cool. All right, let me just take all of this to the side so that I can show you.
Oh my god.
So we start with the original equation, right?
Mm-hmm.
I substituted in all of the e's. So we have the first e, the second e, and I guessed, I wasn't sure, that you integrate with respect to r. I wasn't sure if it was like capital R or lowercase r, but I decided I would try lowercase r. And so you set up the bounds, right? So you have infinity r 0,
Yeah.
and then you integrate. And so then 1 over r squared becomes negative 1 over r with the limits of r and negative or infinity. And then on the other side, you have r squared over 2 with the bounds of
Yeah.
0 and r. And then when you plug those in, right, you can't really plug in infinity, but the limit.
Yeah, it would be 0 there, wouldn't it?
Yeah, exactly. As this goes to infinity. That'd be 0. So then the final result is just negative 1 over r right here. And then on the other side, 0 is 0 minus r squared divided by 2, right? And then you multiply the negatives, multiply the fractions. These r's cancel out. You have 1 at the bottom. And so you're left with these two terms. You add them and you get the result.
Wow. Can you post a screenshot of that in the resources tab on this?
Yeah, I can. I'll make it a little cleaner after this.
Yeah, yeah, definitely. You know, that is that's really clean. Alrighty.
So yeah, I mean, I don't think you want to do that every single time you're asked a question. So I think the best thing would just be to like write down the results somewhere,
Yeah.
and just kind of keep it in your notebook until you need to use it, because
Yeah, this is a very good
it sucks.
yeah, this is a very good a scratch sheet of paper question.
Yeah, yeah.
You know, so here I'm gonna post a screenshot of this, and then I'm gonna say this is lecture 12, slide 6. And then it's going to be chapter 26. It's like kind of, we got to start categorizing things here, you know? So let's see. Or cataloging. That's the word. Okay. Next thing is to find the electric field from the potential, widely used in applications, he says. Finding the electric field from the potential. Oh, okay. So we actually have a little section in this. So in this instance, we're assuming that the E is parallel. So in this instance, it shows 2 points. I and F are separated by a small distance. So the small electric field is essentially constant over a very short distance. Okay. The component of the electric field parallel to the displacement. It doesn't tell us about the electric field component perpendicular to change in x. So wait. If the electric field is parallel to the x-axis, V of B is minus the V of A. I guess that makes sense. So kind of increasing, I guess, from the start position. Electric field in terms of x. If the distance between the points A and B is infinitesimal, the derivative of voltage is equal to the change in voltage, I guess, is equal to negative Ex dx. Perhaps. Dividing by dx. Okay, similarly to the y and z components of the field. This is like differential equation stuff, right? Or derivative of v in terms of x.
Yeah, if you scroll down to page 9 again, you're gonna see the exact same equation, but in right there. Yeah, partial differentiations.
Gotcha. Okay. Shit. Anyway. Electric field along a given direction equals to the negative derivative of the potential along the direction. The potential constant in the region. The electric field is 0 in that region. Okay. So the electric field everywhere is perpendicular to the equipotential surfaces. So makes sense. Okay. E points downhill in the direction of the increasing V. The field strength is inversely proportional to the spacing change in S between the equipotential surfaces. And the equipotential surfaces have equal potential between differences, equal potential differences between them. What? Okay. All right. Equipotential surfaces must always be perpendicular to the electric field lines passing through them. No work is done if a charge is moved along an equipotential surface. A uniform electric field produced by an infinite sheet of charge. The dashed blue lines and the electric field lines are the brown lines. The equipotential lines are everywhere perpendicular to the field lines. So in this instance, is the equipotential lines coming out of the screen in this instance? Like, is this kind of like a cross product rule, orthogonal vector, whatever?
That I don't know.
Because this would be like two different, it's like a cross product thing, I think. I don't know. For a potential charge, the electric field is always perpendicular to the surface of a sphere centered at the charge. Makes sense. A spherical symmetric electric field produced by a point charge The equipotential lines are the dashed blue lines, and the electric field is the brown lines. So equipotential, potential energies. Okay, that makes sense. Equipotential surfaces and capacitors. Equipotential surfaces for two unlike charges. That's right there. At which point is the electric field stronger? A or B? The field strength is the same at both, or there is not enough information. I'm gonna go with, is it A? Yo! That makes sense. Because in this instance, it's a negative correlation.
The slope is flat. Wait, we're looking at V. Okay.
This is the electric field strength.
Oh, okay. Yeah.
Yeah. So with this, it's, I like to think of this as like, you know, like I remember when I was a kid, we did like a thing on gravity, and we grabbed like a tablecloth and put a ball in it. I don't know. It's kind of made me think of that, you know. So it's stronger here, so it's lower. It's a stupid reasoning, but whatever.
Hey man, it
Electron is
works.
released from, yeah, electron is released from rest at x equals 2 meters and the potential shown. What does the electron do right after being released? Moves to the right at a steady speed. Moves right with an increasing speed. Moves left. I'm gonna go with B. Nope. Moves left with an increasing speed. Oh, so it's like pulling it, and then it. Is this like a graph of acceleration, or maybe not acceleration, but velocity? Maybe. Okay. Anyway. An electric field in a region of space is parallel to the x-axis. Okay, so it's parallel, so it's like flat here. The electric potential varies with position as shown in the figure below. Graph the x component of the electric field versus the position in its region shown in space. What? Okay. Slope is contrast. So the electric field potential varies with position as shown. Oh, and that's it for this. Regional space is parallel to the x-axis. The electric potential varies with position as shown in the figure below. Graph the x component of the electric field versus the, okay, does it explain anything in the next PowerPoint? Oh, this is the same thing. Nope. Okay. I guess it's going to ask us about what's on quiz 2 now. Let's see. The force on charge Q to the charge Q1 is force 1. If Q2 is equal to the net force on Q is equal to. Oh yeah, that's 0. So there you go. Two Gaussian spheres 1 and 2 are surrounding charge Q. The radius of the sphere 2 is 2 times larger than the radius of sphere 1. What is the flux of the electric field through sphere 2? should be the same. It's the same amount of electric field kind of vectors going out of the sphere. Oh, these are all like fun little quiz questions. Do you guys want to keep doing this one, or do you just want to move on?
I think you should do it because I think that same question was on the exam
Okay.
or something like
Sure.
that.
Yeah, that's good. There are two solid spheres, 1 and 2, carrying the same charge Q. In both spheres, the charge distribution is uniform. The sphere 1 has radius r, while sphere 2 has radius r2 is equal to 2r1. So it's double the size of r1. Sphere 1 creates an electric field at E1 at a point of distance r is equal to 4r1. Okay. 4 times the size. So, 4 times away from the center of the sphere, or 4 times the radius from its center. What is the electric field E2 due to the sphere 2 at the same distance from its center? Wait, we did the. Can we see our quiz answers for this? I'm kind of swinging for. I feel like this kind of has two right answers because you could say it's the same electric field as 1. Oh, it's A. It's the same electric field because they have the same charge. All right, so perfect. Thank you for the screenshot. Alrighty, let's see. Quizzes. Was this quiz 3 that we did this one on? Oh no, it wasn't. Quiz 2. Yep, it's that one.
Yeah.
E2 is equal to E1. Okay. Charge Q positive is placed inside the cavity and initially uncharged conducting sphere. As a result, the charge QS at the outer surface of the sphere is equal to what now? That's B. Because you'll have the negative charges on the inside here, and then you have an equal but opposite charge on the outside.
I agree.
Good conceptual questions. Yeah, those are good ones. Lecture 13. Okay. So this says, due to a charged conductor, consider 2 points on the surface of the charged conductor as shown. E is always perpendicular to the displacement. That makes sense. Therefore, E dot product with the ds is always equal to 0. Therefore,
I don't get that.
Difference. Well, I'm assuming D of S is.
It's the surface. And yeah.
Isn't it that if they're parallel, they should be equal? They should be 0?
That's for magnetic. We're not there yet.
Okay.
This is electric.
Therefore, the potential difference between A and B is also 0.
Yeah, because they're both 0. So 0 minus 0 is 0.
B is constant everywhere on the surface of a charged conductor in equilibrium. The change of B is equal to 0 between 2 points on the surface because, yeah, it's equal. The surface of any charged conductor in electrostatic equilibrium is an equipotential surface. I mean, yeah, the charges are going to be evenly distributed. So, let's see. Let's see what I got. Hold on.
That checks out. Because the electric field is zero inside the conductor, electric potential is constant everywhere inside the conductor and equal to the value at the surface. Okay, I suppose.
Alrighty, give me a quick second. So the point on the surface charged conductor in equilibrium is the same as the electric potential. So we recall this because the, okay, hold on, the family is leaving. Give me a second. Okay. Let's see. So every point on the surface of a charged conductor is equilibrium at the same. Okay. Because the electric field is zero inside the conductor, the electric potential is constant everywhere inside the conductor and equal to the value of the surface. Okay, this like the more I read this, the less I'm understanding it. Like,
Do you want to try explaining the last sentence?
you want me to try to, or do you want? Wait, what? Say it
That
again?
one, the one in red.
You want me to explain? Is that what you said?
No, do you want me to try to explain it to you?
Oh, sure, yeah.
Um, so do you know how when you have a linear slope, the derivative is constant, meaning it's zero?
Yes.
Right. So if there is no change in the electric field, the derivative, right, thus the potential is zero. And so if it's constant everywhere inside the conductor, then it is equal to the value at the surface because it's constant everywhere.
Okay. I can see that. That makes sense. Okay, and that's what this is saying. dv over
Yeah.
d of x is equal to 0 is the derivative of the voltage and in terms of x is 0 all over. Okay, makes sense. It's these kinds of notations that I've always struggled with. I think it just doesn't click that well for me, and it just makes it worse. I think when I see them. But anyway, in this thing, charge density is high when the radius of curvature is small, and low where the radius of the curvature is large. The electric field is large near the convex points, having small radii of curvature and reaches very high values at sharp points. This just makes sense because if the charge is distributed amongst the surface of the conductor, the areas that have the most surface area are going to have more particles. So,
Yep.
makes sense.
Makes sense to me too.
A conductor of electrostatic equilibrium. When a conductor is in equilibrium, all excess charges it's on the surface. The surface is an equipotential. Okay, this electric field inside of the conductor is 0. The external electric field is perpendicular to the surface. At the surface, that makes sense. And then the electric field is strongest at sharp corners on the conductor surface. That makes perfect sense there. Now, a large charged conducting plane. So consider a large charge conducting plane, sigma equals Q over A. That's sigma, right? Or is that sigma? I don't,
I don't know. I have no idea.
I guess we'll see. So sigma is charge divided by the unit area. That looks more like you're finding a charge density question. So find the electric field using Gauss's law. So electric field points straight away, both above and below the surface of this plane. Thus, wait, is this, wait, which notation? Sigma. Fuck, I don't know what. All right, anyway. This thing is equal to 2 times the electric field times the area, and the enclosed charge is the
Surface density.
surface density. That's what it was. Is it surface charge density or is it just surface density?
I think it's surface charge density.
Okay, surface charge density.
Yeah, surface charge density.
Okay, this makes perfect sense. This right here.
That's
This
Gauss's
is
law. And
Gauss's
the
law.
little, the strange symbol is the symbol for flux.
Gotcha. Okay, let's see. Gauss's law says, oh yeah, duh, it says it right here. I should read beyond the line I'm looking at.
No, dude, that's for nerds. We don't read.
Exactly. 2EA. Oh, so you just set these things equal to each other. This is kind of a alteration of it's probably not an alteration of Gauss's law, but a kind of like a remix.
Yep.
So 2EA is equal to that times the area over epsilon naught. And that is for a large charged conducting plane. And we have to remember that this is equal, this is our charge density, like you said. There it is. It says it right there. I could have just put it there, but anyway, E is equal to, I mean, this right here, all this is just rearranging this for the sake of putting it in terms of E. That's all.
Yeah.
It is.
And so this only works for a plane.
Okay. I'm gonna screenshot this. I feel like this is gonna be useful. Let's see. Lectures 13, slide 10. I think this is also still chapter 26.
Yeah.
I'm gonna say, yeah, chapter 26. Anyway, energy of a charge distribution. So we have a parallel plate capacitor. So you have a positively and a negatively charged field. The fields behind the planes cancel. And then you have an added field between the two. So the electric field, E of charge density over epsilon equals all that. This is the same as this up here. No, it's not. This is 2 different planes, so it would interact differently. The electric field is equal to E of the surface density over epsilon. And
This is the same thing we talked about earlier. Like if you notice, it's the same formula, E equals Q, which you have written down in your paper somewhere, over epsilon naught times A.
Oh, is it this one right here?
A little higher in the blue section.
Oh, it's in the blue section.
Yeah, you see that, E of S.
Oh yeah, this right here. Oh, look at that. Okay.
It's just another way to calculate the electric potential, but only for a parallel plate capacitor.
Oh, you're talking about this one, potential difference, this formula.
The one above.
Oh, you're talking about electric field?
Yeah,
Okay.
and then using that in this, I guess, example, that's how they, um, I guess, not differentiate, derive the potential difference.
Gotcha. Oh, I see here. Yeah, because you have the potential. If you had this in terms of E, it would be potential difference over the displacement. Displacement. Yeah, displacement. I think so. And then this, yeah. Ooh. Okay. Makes sense. And then you have the potential difference, which is that potential difference here is more related to this, except it looks like D in this case. Oh, D is probably the whole thing. So E is equal to charge density over epsilon. Okay. So it looks like for this parts right here, they just kind of like broke it all down, plugged in E, and then when they plugged in E, they replaced charge density with Q over A. That makes sense. And so if we're moving an additional very small positive charge dq from the negative to the positive plate, so from here to here, we need to do work against the field. This is negative work, okay? How much work?
But I fucking hate work.
I hate work too, yeah. So dw, so the kind of derivative work charge or whatever, is negative v. It's the negative this thing, because you're going from one all the way to the other one. So this whole formula, this thing, that's what it is. That's v. What is v? It could be velocity. We don't know, but it's
Definitely.
just. I think that if this is kind of like, again, like you said, like this question we were looking at up here. If we had to go halfway to like an s, then this wouldn't just be negative v. It would probably be just negative s. Because then it's work up to the just this work, I guess. I don't know. We could leave it there. We can use this expression to calculate the total work needed to charge the plates. Okay. Parallel plate capacitor. The total. So, this is just the math for it. So work is the integral of V in terms of Q. So it looks like they pulled out everything but the Q. That becomes Q squared over 2. Put it back with everything else, and that's your formula. That doesn't seem too bad. That is probably the easiest integration we've done here so far, I think, in my opinion. Straight point. All right. Parallel plate capacitor. Let's see what we got. All right. The work done in charging the plates ends up as stored potential energy of the final charge distribution. Potential energy is the negative work, which is this. So that's your formula for the work done charging the plates. Where is the energy stored? The energy is stored in the electric field. Yep. Interesting. Okay. Parallel plate capacitors. The energy potential is stored in the field in the region between the plates. So this is a continuation of the above question. is equal to epsilon naught over 2. Whoa. Oh, so we just replaced Q with epsilon times electric field times area. It's an interesting way to go about it. Okay.
So many equations.
There's a lot of equations to look at. I just want to make sure I'm like kind of internalizing it.
Yeah, no, same.
Okay. Is this shown above at any other point? I don't think so. It's just assumed like we already have to know this, I guess. Capacitance. Yay. Two parallel plates charged Q and negative Q respectively constitute a capacitor. Respectively. The electric field between the plates is electric field is equal to Q over A epsilon naught. Potential difference between the plates. So that one. Charge Q gives rise to potential difference V, such that V is equal to that. So if we divide both sides by Q, we would get capacitance is equal to D over area times epsilon. Is that right? C equals QV. Parallel plate capacitor. Well, then Q gets replaced with epsilon, not, huh? The capacitance is directly proportional to the area of the plate and inversely proportional to the separation between the plates. So it looks like as there is more separation between the plates, capacitance drops. As there is less separation, capacitance increases. As the area of the plates increases, so does capacitance, and as they decrease, capacitance also decreases. C equals
Sick.
QV. Say again?
Sick.
Gotcha. Let's see. I'm gonna try, but it's not true to large proportions.
I don't know how Q is always proportional to V, but that's fine.
Yeah, right. If you're dividing it by V. I don't. Well, in this instance, it's just. I have no fucking idea. Okay.
It's okay. It's probably just because charges cause potential differences, but that's okay.
Yeah, that could be it there. What does a capacitor do? A capacitor stores electrical charge and stores electrical energy. Capacitors are basic elements of electrical circuits, both macroscopic and microscopic, as parts of integrated circuits. Capacitors are used when a sudden release of energy is needed, such as in a photographic flash. Electrodes with capacitor-like configurations are used to control particle beams, ions, and electrons. How neat is that? Who would have thought that all this work, all for a camera flash? That's crazy. Anyway. Should we do one more slide presentation?
Yeah.
We've been at this for about an hour and a half now. Or should we try to muscle all over?
No. I'm literally after this one. I'm gonna go because I'm
Yeah.
fucking exhausted of this already.
This is already getting me really fucking tired. So yeah, maybe like we'll do this last.
We can do
17.
We can. I mean, if you want to do like 4 or 5 lectures, these I mean, if we do 3 or 4 lectures every day, that we'll be done with them before for the start of the next week. So
That's true. And this is a little, we don't want to burn ourselves out either. So, we want to be.
Plus, I still need time to digest whatever the fuck was said in class today.
True. Yeah. Today was. I need to look at the slides, definitely.
Yeah, I was way too fast. Way too fast.
Yeah, it was pretty crazy. But all right, let's see. Let's get her done. Lecture 14, continuation of capacitors. But
it's literally the same slide.
Yeah, now we're going to look here. Energy stored in a capacitor. So the potential energy stored within a capacitor is Q squared D over 2. We already did this one. And for a plate capacitor, it's a little bit different. It's just area epsilon naught over displacement, I'm assuming.
D is the distance between the 2 plates.
The distance between the 2 plates. Okay. And then you have potential energy is Q squared over 2. So this is a simplified version. If you need capacitance, which is also equal to 1/2 CV squared. Okay, fine. This energy could be obtained by work done to convert some other kinds of energy into the electric one. What sources of that energy? Conversion of mechanical, chemical, or solar energy into electrical energy. All such devices create a potential difference, which means source of energy to use it is numerous in applications. Lead acid battery. This is honestly, this is probably one of the more interesting classes that we had, at least for me, because
you like batteries, kid?
I think batteries are super neat, sulfuric acid molecules. Yeah, we were looking at batteries for a little solar array that we're building here, and it, aside from how expensive they are, it's crazy how many kinds of batteries there are. So plus eating batteries is fun. So
Oh yeah, man.
Okay. Oh my god, what
yeah,
is
no,
this?
that I looked at that and I'm like, I don't think I want to go past this. So that's why we should call it after this one.
Okay. So this is really just a very detailed breakdown of how a lead acid battery works.
Yeah, I don't know, but I don't think it's worth looking at.
Yeah, I'm not going to spend too much time on it. It's fun to know, but no thanks. Not now. Electric field and dielectric materials. So dielectric materials or electric insulators are materials in which all the electrons are bound to atoms.
Okay, I'm gonna write that one down. I did not know that.
So good electric fields, or I'm sorry, good insulators are things like glass, quartz. I'm gonna throw in an example I think is a good one. Maybe rubber. I could be wrong, but as far as I know, rubber is a pretty good insulator. Molecules are said to be polarized when a separation exists between the average position of the negative charges and the average position of the positive charges. Basically, something is polarized when the charges are kind of all out of whack. Polar molecules are those in which this condition is always present. Polar molecules. Okay. Molecules without a permanent polarization are called nonpolar molecules. Is this kind of like what we did a couple weeks
Today.
ago with the dipole moments of like water molecules, and like one side is positive, the other side is negative?
Yeah, I think that's actually in these slides.
Yeah, okay. So here we have the polarization of an atom induced by an external electric field. So as you can see, fuck, I don't electric field going that way. So the negative gets attracted this way, and this creates a polarization. The negative particles in this are pulled to the side, causing a net positive force on this particle. And it's doing something, it's like stretching it, it's, think of it like the magnetic goop stuff you see on TikTok. Anyway, this is there it is. Polar molecules have their own dipole moment regardless of the external electric field. So electric fields align molecules in such a way so that their dipole moments are parallel to the field. I didn't even read ahead and I figured this out. Look at me. That's awesome. This, I think, starts getting into the conversation of torque. So the dipole moment P is at an angle theta to the field, causing the dipole to experience a torque. Each charge experiences force F is equal to QE. The net force on the dipole is 0 because the forces are of opposite directions. Dipole will not move as a whole in the electric field. Forces are applied to different parts of the dipole, and torque may not be 0. Torque is the cross product of R and F. So in this instance, I do not know what R is, but I could tell you that F is the movement of this particle, and R, what is that, rotation or something? Radius? Maybe it's radius.
I don't remember where, but in one of the lectures, we went over over dipoles, and there was a formula that came out of it. But we don't need it. It's okay.
Okay. We'll see if we can find it at some point to maybe get written down, but this is another example of polar molecules in a solid/liquid state being affected by external magnetic fields or electric fields. Electric field. Kenny says, isn't the exam in 11 days? It's on the 19th, Kenny. Okay, my keyboard turned off. I can't type it. Anyway, suppose we fill the space between the plates of a capacitor with an insulating material, a dielectric. The picture will be shown above regardless of the polarization mechanism. The electric field due to the plates is directed to the right as it polarizes the dielectric. The net effect on the dielectric is an induced surface charge that results in an induced electric field opposite to the external field. Right? It reduces the total field inside the dielectric. The induced charge density on the dielectric is less than the charge density on the plates. We define the dielectric constant. K is for dielectric, apparently. Constant is the electric field naught, so it's 0, I'm guessing, divided by the electric field, just the electric field. The dielectric constant is a property of material. is a constant property of the material. Easily polarized materials have larger Oh, there it is. So in this case, R is
Um, don't ask me, bro.
that was good. No worries. Easily polarized materials have large dielectric constants than larger dielectric constants than materials not easily polarized. Vacuum has K equals 1 exactly. Filling a capacitor with the dielectric increases the capacitance by a factor equal to the dielectric constant. So C is capacitance, and yeah, equal to that. So it looks like if you were to have a dielectric inside of a capacitor, what you would do is you would divide the bottom by K, which makes sense because I guess in a way you are you're increasing the capacitance. So the way you can do that is by decreasing the denominator. Or in this case, the way they do it, multiply it or multiply capacitance by the dielectric constant. I actually saw a video of someone taking apart a regular AA battery, and this is exactly what it looked like. And when I saw that, it kind of like, I don't know how to describe it. Like it just feels like, I like to think we're like in the future and stuff, but we really are out here just wrapping like aluminum foil with paper and electrifying it. So that kind of is concerning sometimes. It's just weird to think about.
It's science, bro.
Science is crazy.
Bitch.
See if I can find like a picture of it now. You got me thinking. But anyway, let's keep reading. The breakdown of the electric field of air is that, which is pretty interesting, I guess. But AA battery. I thought I would be able to find it. I guess it makes sense that there's probably not the exact video that I'm looking for, because if you rip open a AA battery, it also catches on fire. So, but I swear to God, it was so weird. Anyway.
What do batteries taste like?
Spicy. I don't know. Look at this guy. He opened up a battery.
Oh shit.
He ripped out some wacky thing. And that right there, does he pull out the whole thing? No, he can't.
Isn't that like super dangerous?
Yeah. Pull out that thing. This is like the wrapped stuff, I think. It should be, at least. He's getting like the battery stuff all over his hand too. In this video.
Yeah.
Anyway. Well, that was exciting. Yeah. Look, this is it. This is it. This is what I'm telling you. Look. Just unwraps it, and it's wrapped up aluminum foil. Like, look at that. That's all this is. It's a fancy version of it. Anyway, enough looking at weird things like that.
That's pretty cool.
Yeah. Dielectric constant, dielectric strength. What is this useful for? Great question. So dielectric constants. Wait, what is that again? Property of a material and how easily it gets polarized. There you go. He'll give you this if you need it. A two-plate capacitor has plates of areas 10 centimeters. That calculate the capacitance of the capacitor. Fill the space between the plates with Teflon. What is the capacitance now? So I'm assuming he just gives you the basic capacitance formula here, and then we have to figure out how to do it. And then he says, how a dielectric filling affect the energy stored in the capacitor Y. It affects the energy in that the capacitance increases. soon. All right, so that's my best bet there. Anyways, that concludes lecture 14. So I guess maybe tomorrow we could hop back on and do 14, lecture 15, 16, and 17 or something. So we can continue our review sessions.
Yep.
I guess I'll start at around 8 again tomorrow. I'm also going to try to review ahead a little bit. That way I'm not so like, what in the world is all this, you know, but that is my plan. So anyway, it was fun. Hope you all have a good night. All two of you. And, all right, I'll see you all in the next one then. All righty. Stop sharing.
Bye.
Tomorrow. Bye bye.
Bye.
Thanks.